So we finally get to apply the idea of a limit. We've been finding limits for a while now, and now let's talk about what they're actually used for. The first application is what we call difference quotient. And this is just a fancy way of using a limit to find the slope of a function. Now, you guys have been learning about slopes for years now. In terms of linear functions, rise over run, how much is the change, delta y over delta x. When we talk about a nonlinear function, hopefully you can see it's not as easy because this section of graph probably has a different slope than this section of graph. So we can't just say it's a single number. And that's where the limit will come in. Okay, so let's say I would like to pick an arbitrary value and I would like to find the limit at that point. Okay, I'm going to call this point x f of x, just to generalize it a little bit. So it looks like it's around 1. I really don't care. I could have chosen any point. Now, if I'm going to find the slope, I have to compare that to another point on my graph. So I'm going to choose another point. I want it to be really close to my original. And actually, I just want it to be h units away from the original. Okay, so again, h is an arbitrary number. We want h to be really small, though, and that way our 2 points are as close together as possible. Now, we want h to be so small, it's basically going to be 0. And the only way we can force that is to use the limit and make h get really close to 0. Okay, so this is the first part of our difference quotient, is a limit as h approaches 0. Now what we're going to do is just use our slope formula. Slope formula says y2 minus y1. So y2, which is f of x plus h, minus y1, which is f of x, and then over x2 minus x1. So x plus h is my x2, and my first x was just x. Hopefully you can see in that denominator that the x's would zero out, so they're gone. So this leaves us the difference quotient, which is now the limit as h approaches 0 of f of x plus h minus f of x over h. So applying this limit to any function will give us the slope in terms of that function. Okay? Okay, so let's give it a try. Now, I have two different examples for you here, one more complicated than the other. First one is just a linear function. So you should be able to look at this and say, hey, why do we even have to do this? I know my slope is going to be 3 because a line has a slope of m, right? But I just want to show you how the difference quotient would work. So I'm going to start by actually finding just f of x plus h to start out. Okay, when you see f of x plus h, that just means go to your function, and anywhere there's an x, we're going to substitute in x plus h. So it's not 3x plus 2, it's 3x plus h plus 2, which simplifies into 3x plus 3h plus 2. Okay, so that's the part of the difference quotient that says f of x plus h. Okay, so now let's get into it. Limit h approaches 0. F of x plus h was that thing right there that I just found. So 3x plus 3h plus 2 minus f of x. F of x is just our original function, so 3x plus 2. Then all over h. Okay, so now let's do a little bit of simplifying. I can see here just with the subtraction that the 3x and the 3x are going to subtract out. 2 and the 2 will subtract out. So it looks like just with the subtraction, I have the limit as h approaches 0 of 3h divided by h. H's will cancel now, leaving me just a single value of 3. And isn't that what we said it should be? This line has a slope of 3, just like the difference quotient is telling me. Okay, now let's get a little more complicated. And it's actually so complicated, I need to go with a smaller pen so I have room to write it all. So I want to start by, again, finding f of x plus h for this radical function. Okay, so f of x plus h is just plugging in x plus h into my radical, where the x was. Okay, so it's 2 square root x plus h plus 5, and that's what will be in my difference quotient. Okay, so I'm going to find the limit as h approaches 0 of f of x plus h, which I just found, 2 square root of x plus h plus 5, minus my original, which was 2 square root x plus 5, and then all over h. Okay, with the subtraction again, we can see that the 5 is going to cancel out the 5, but that's really all that's changing right now. So I still have the limit as h approaches 0, 2 square root x plus h minus 2 square root x over h. Can I go ahead and use direct substitution? Can I plug in the 0? This would give me 2 radical x minus 2 radical x. That's a 0, and a 0 on the bottom. So at this point, if I were to do direct substitution, we get indeterminate 0 over 0. Instead, think about what type of expression we're looking at. This is a rational expression with those radicals in the numerator. So let's unrationalize it. Let's use that conjugate to move it back down to the bottom. Okay, so I'm going to go ahead and multiply top and bottom by the conjugate, what I'm looking at right now, which would be 2 radical x plus h plus 2 radical x, top and bottom. All right, so when you see those radicals, think about your conjugate. Okay, so what's happening? Still got my limit hanging on, haven't done it yet. When I do first times first, the 2 times the 2, be careful, will give you a 4, but the radical will cancel. Minus, outsides and insides cancel because they are conjugates. Last times last, again, be careful, the 2 times the 2 makes another 4. The radical x just makes x. Over denominator, I'm not going to multiply out because I'm hoping good things will happen here in a second. So h, 2 radical x plus h plus 2 radical x. Okay, so do you see what's going to happen in that numerator? We're going to have a 4x hanging in the front. We have a minus 4x in the back. So the 4x is gone. I still have that 4h though. Okay, so limit, h approaches 0. I've got a 4h on top, and that's okay because there's an h in the denominator. Plus h, 2 radical x. Okay, so now I can cancel the h out of numerator and denominator. Once I've canceled those h's, once those go, you should be able to go back to direct substitution. Do you see how you can now plug 0 in for that h and everything's okay? Okay, so last step, plug in that 0. It looks like we're going to get a limit of, there's a 4 in the numerator. We're going to have a 2 radical x plus another 2 radical x. So just in cleaning that up a little bit, I've got a 4 over 4 radical x, which equals 1 over radical x. Okay, this is actually going to help us determine the slope of any point on that function. Okay, remember, as this function is changing, if you were to graph it, the slope changes depending on where you are in the function. So this is just a little formula we can now use to help us find slope. I've given you a specific x value I would like you to find the slope at. So at x equals 3, I would now plug in my 3. The slope is 1 over radical 3. Or if you want to rationalize, radical 3 over 3. If we were to choose another value of x, we would get a different value for slope. But that's what that difference quotient does for us. It helps us find the slope at any point on the graph.